We can take a look at three different states of matter and how they can change between each other by changing pressure and temperature. We'd seen when talking about ideal gases that gases become less ideal if the temperature is decreased or if the pressure is increased. This is because increasing pressure forces gaseous particles together to the point where they come closer and closer, that their interactions increase, that start behaving more like a liquid. So we could see that if you increase the pressure on a gas, it can become less and less like an ideal gas, more like a real gas, and then finally a liquid. Similarly, by decreasing the temperature, we can turn an ideal gas into a real gas into a liquid by having the particles come closer together with a lower temperature. Volume is decreased, but also because at a lower temperature, the relative importance of the interactions increases as well. The particles cannot stay in their high energy states as much as before. So you can also turn a liquid into a solid, increase the amount of intermolecular interactions by cooling temperature as well. Okay, so this is the phase change diagram for carbon dioxide. We can see that gas can turn into liquid or solid, or liquid can turn into solid, or vice versa, etc., etc. So consider that at 1 atmosphere, we have several possibilities for the condition of carbon dioxide. If it's at 1 atmosphere pressure, then it's either just solid or gas. Now, when its temperature is increased beyond negative 78 degrees Celsius, that solid turns into gas. It sublimes. You actually can see this here. Here, carbon dioxide solid, dry ice, is put into a small plastic pipette, and it's allowed to warm gradually in a container of water. Now, you can see that it goes straight from solid into gas. It does not turn into liquid. Yet, as that occurs, though, the pressure is increased within that container to the point where it's now above 5.2 atmospheres. It's above the triple point. So that now, having this higher pressure, solid actually turns into gas. You can see that within this container, now having a high pressure, that solid turns into liquid, solid into liquid, so that we have now just liquid and gas. And then eventually, as more of that liquid now turns into gas, it has a pressure buildup and the plastic explodes. So for those of you in my high school chemistry class, you'll be dealing with this explosion soon. So we see a couple interesting points here. We have the triple point, at which we can have a mixture of solid, liquid, and gas all at the same time at equilibrium. So that's kind of halfway in between where all this solid is turned into liquid. So here we have a mixture of gas, liquid, and solid. We're at the triple point. And then also interesting is the critical point. If the pressure is increased enough, then it is impossible to have pure gas or pure liquid when we're in this region with regard to temperature and pressure. Having this critical fluid, there are new properties possible for this carbon dioxide. This critical fluid, the supercritical fluid, is able to help extract caffeine from coffee beans and has some other kind of properties as well, besides just those of a typical liquid or gas. Okay, so at this point we have the critical pressure, and at this point we have the critical temperature. So it is, if you are above the critical temperature and the critical pressure, you will have a supercritical fluid. All right, so we see that with carbon dioxide, the slope between the solid and liquid is positive. We can see that increasing the pressure on liquid, which will typically increase the density by pushing particles closer together with pressure, we increase the density. That turns liquid into solid, as with almost all substances. Yet, when we take a look next at water, we see that increasing the pressure should therefore increase the density, and actually that turns solid into liquid. Water is special in that the most dense form of water is actually liquid instead of solid, unlike almost all other substances. So water is typical for this negative slope between solid and liquid. A couple other interesting points. We have here, let's see, 1 atmosphere. If we're at 1 atmosphere pressure, what temperature does solid turn into liquid? What temperature does water freeze at? 0 degrees Celsius. This is known as the normal boiling point. When we say normal boiling point, we're meaning what is actually melting point? What is the melting point at normal atmospheric conditions, aka at 1 atmosphere? And we also have at 1 atmosphere here 100 degrees Celsius. This is the normal boiling point. This is the boiling point if we're at 1 atmosphere. Okay, thank you for watching, guys.